Hello. Today we're going to do Newton's method and Euler's method. They're two separate methods. We're going to do Newton's method first, go through an example, and then we're going to do Euler's method second and go through an example. Okay, so Newton's method. It's a way to find successively better approximations to roots, which are also known as zeros, of a function. So if you didn't know what the actual zeros were, if you couldn't factor it, a way to find zeros is this awesome Newton's method. And you have this formula and you can just keep going. The number of iterations that you do, it keeps getting closer and closer and closer. It's pretty nice. Okay, so you have this x sub n plus 1 is equal to x sub n minus the function value at x sub n divided by its derivative value at x sub n. And it goes with tangent lines. I'm going to explain just how it works in a bit. The way to do it is you're going to start with an x sub 0, and that is your guess for what the root might be. You just kind of look at it and try to figure out, okay, what number might be close to the root. I'm going to scroll up for a bit more space. Okay. So what you're going to do is you've got some curve. You might not be able to graph it. You're usually given like a function formula. And what you're going to do is guess where the root might be. So say you make this as your guess for where the root might be. Well then, you plug that value in and you get a function value and create a tangent line at that point. That's what the formula does. It does that for you. Creates a tangent line and gets a new x value. And that new x value is closer to the actual 0. It's pretty cool that just by doing that, you're, boom, able to get a lot closer to the spot that you're looking for. It's cool. As you use the method more and more, you get closer and closer. So if you start all the way over here, and you've got your function value, tangent line, boom, new x value that's closer. And then that function value, tangent line, new x value that's closer. And those are the x values on the axis. And the x-axis, that intersection is where the zeros are. And oh my. So each time you do that, function value, tangent line even closer, function value, tangent line even closer, every iteration is going to get you closer to that root. So we are going to do a problem. I'm going to use two iterations of Newton's method to approximate the positive root of f of x is x squared minus 2x minus 1. That's not factorable. We wouldn't be able to find the root by factoring. Of course, we could use quadratic formula, but we're gonna go for Newton's method here. Okay, so the things that I need the function, I need its derivative, we're good at that, and I need a guess for the root. Now, it actually doesn't matter if you start above or below what the actual root is. Looking at this, I look at, okay, if I plug in 2, I'm going to get negative 1. That's pretty close to 0. Let's start there. So I'm going to start with my x sub 0 is 2. My f prime is 2x minus 2. My f of x, x squared minus 2x minus 1. Those are the things I need to start. So let's work with this. Okay, so the formula, x sub n plus 1, if I start with x sub 0, 0 plus 1 is 1. So x sub 1 is, and then I've got x sub 0 minus, and then the function value at x sub 0 divided by the derivative value at x sub 0. So that's what we're doing there. I'm going to plug things in. So x sub 0 is 2. X sub 1 is the new x value that's closer to the actual 0 that we want to find. So I've got, x sub 1 is equal to, x sub 0 is 2, and then minus, and then f of 2 divided by f prime of 2. Okay, so this is 2 minus, and then f of 2, if you plug 2 into the function, you get -1. And if you plug 2 into the derivative 2x minus 2, you're going to get 2 there. So we've got 2 plus 1/2, 2.5. So that's our new x value. So 2.5, well, that's the next one. Okay, so that's our x sub 1. And how many iterations are we doing? Oh, 2 iterations. So let's do our second iteration. Okay, so now I'm going to start with x sub 2. And I'm going to be doing the x sub 1 minus f of x sub 1 divided by f prime of x sub 1. I'm going to plug into there. So x sub 1 is 2.5. So 2.5 minus the function value at 2.5 divided by the derivative value at 2.5. So we're working through that. X sub 2 is, okay, so 2.5, and then minus f prime of 2.5, we get 1/4. Oh, sorry. Ooh. F of 2.5, we get 1/4, and then f prime of 2.5, we get 3. So we're looking at 2.5 minus 1/12. Okay, well, let's do some fraction fun. 2.5, that's 5/2. And we're subtracting 1/12. So I want a common denominator. I can multiply by 6 here and get 30 over 12 minus 1 over 12, which is 29 over 12. So that's the new x. We're just looking for 2 iterations on this problem. So this is going to be my approximation for the root after 2 iterations. So let's look at what that is approximately as a decimal. I got 2.417. And you know what's really cool? If you graph the original problem and find the positive 0, you get that the actual 0 is 2.414. How cool is that? That is so close, and that's just 2 iterations. If we did one more, we might be able to get it perfect to 3 decimal places. Who knows? I think it's really awesome. Okay, we're going to do Newton's method next. No. That was Newton's method. We're going to do Euler's method next. Even when I talk to myself, I'm a little crazy. Okay. Woo! So Euler's method, we're going to use it to approximate solutions to a differential equation. Sometimes you might have a differential equation and it's one that you can't actually solve and get a function for. But you can still find values that are close to the function. And what we're going to do, you're going to start with the derivative. You have a differential equation. It's giving you the derivative. And if you have 1 point from the original equation, you can then use that to write the equation of a tangent line. And then that tangent line, you're going to use it to get another point that's really close by. And then that new point, you'll write another tangent line because the slope will be different at that point. But you're going to use the slope from the differential equation. And you're going to keep going. I'm going to show you a picture. Okay, so the blue is the actual curve but when you're doing these problems, you might not know the actual curve. But you start with a point. And since you have the derivative, you can, with a point and the slope, write a tangent line. And that tangent line goes forever, but you're just going to go a little bit out and take a new point. And at that new point, you're going to figure out what's the slope of the actual function at that new point, and do a new tangent line, and then pick another point, and keep going. And while it's not perfect, if you do really itty-bitty steps for each of those new points, you can get darn close. It's pretty cool. Okay, so we're going to use Euler's method with a step size of 0.1 to approximate the value of y when x is 1.3. Given the derivative, dy dx is x minus 2y. Notice that's not one of the separable differential equations that we know how to solve. And the point 10 is a point on the curve. So if you have 1 point on the curve, you can use this Euler's method. Okay, so how do I write the equation of a tangent line? I need a point and I need a slope. So let's start with our point. Our point is 1, 0, and our slope comes from the derivative. It is x, which is 1, minus 2 times y, which is 0. I'm using the dy dx formula to get the slope. So the slope here is 1. Okay, if I have a point and a slope, I can write a tangent line. So we have y minus the y value is equal to m, right there, and then x minus the x value. Or y is equal to x minus 1. Okay, well, we're doing a step size of 0.1. So this is when x was 1. So my next step is going to be x is 1.1. Okay, so now I'm looking at x is 1.1. Well, let's plug that in and see what this tangent line says for the y value. So our y value is approximately the x, 1.1, minus 1, or 0.1. So I have a new point. X is 1.1, y is 0.1. Now this point might not actually be on the original function, but it's as close as we could get with the info that we had and the step size that we're given. I'm going to start from scratch now with this point and get a point and a slope and write a tangent line. Okay, so point, let's do slope, dy dx. What's that going to be? It's x minus 2y. So the x is 1.1 minus 2 times the y, 0.1. Yeah? And so our new slope is 0.9. Let's write a tangent line. So we have y minus the y coordinate equals m, the slope, 0.9. And then x minus the x coordinate, x minus 1.1. So I'm going to use that tangent line to get my next point. We just used x is 1.1. So if I'm doing a step size of 0.1, my next x is 1.2. I'm just going up by 0.1 for the x value. So now I know that y minus 0.1, this is going to definitely approximate here. Okay, we have a 0.9, and I plug in the new x, 1.2. I'm using the tangent line to get a new approximate y value at x is 1.2. Let's see how that goes. Okay, so if I add this, we've got an approximation, going to add the, I don't need to put a plus there, 0.1, and then subtract those. We've got a 0.09 when you multiply that. So our y approximation, 0.19. So that gives us a new point. Oh my. Whew. We just had 1.2 for x, and we got out 0.19 for y. I'm going to use this new point to do a tangent line. Yeah, it's a little tedious. A little. But I kind of like it. Yeah. Okay, we have a point, let's get the slope. dy dx equals, woo! Okay, x, which is 1.2, minus 2 times y, which is 0.19. Our slope here, 0.82. Fun slope. So I have y minus the y coordinate, 0.19, equals m, the slope, 0.82, and then x minus the x coordinate. That's our tangent line. I'm going to use that tangent line to approximate the y value when x is 1.3. I'm about to be done. Okay. So y minus 0.19, we've got 0.82, and we want to know when x is 1.3. Okay, let's work this out. Y is approximately, let's add that 0.19 plus 0.082, fun stuff. Oh my. So I get 0.272 for our approximation of the y, oh, fun. Okay, y of 1.3 is approximately that. So I started off with a derivative, the rate of change, and a single point. And then I went step by step, finding the slope at those different points to try to get to what the actual y value might be at 1.3. Is this exact? No. If we did like 0.01 for our step size, would we get closer? Heck yeah. But that's what we got. That's Euler's method. Newton and Euler, pretty smart people. And I hope you have a delightful day.